In class, I mentioned that the 5 kinematic equations can basically all be derived relatively straightforwardly with just some algebra. Not particularly pretty algebra sometimes, but just some algebra. But it isn't strictly necessary for using them. So I offloaded that to this video. If you're interested in why these equations look the way they look, then you can follow along. If you're satisfied that it can be done, then you actually probably won't lose that much from not worrying about it. We will start with the assumption that the acceleration is constant. So a is a constant. That gives us sort of our first and goofiest one, which is that if a is a constant, then the average acceleration is also just equal to a. If some number doesn't change, then its value is its average value. And that can be explained mathematically, but seems far more work than it's worth. I think is relatively straightforward. The average of a number that doesn't change is itself just the number. So then we say, well, but the definition of the average acceleration is delta v over delta t. So if we assume that we are starting at t equals 0, and we have measured x0 and v0 as the position and velocity at that time, then we can go back to here and say that our average acceleration is a, and our delta v is v minus v0, and our delta t is t minus 0. Remember, the v sub 0, or v naught, is the velocity value at t equals 0. It doesn't mean that v is 0, but really, when our clock starts, v0 is the speed. And t0 technically would be the starting time, but we're going to set that to being 0. And that allows us to sort of simplify this expression a little bit, and we get v minus v0 over t. And now algebraically, we can just bring the t to the other side. So I have at equals v minus v0, and ultimately that lets me then rearrange this and say that the velocity at any time is the velocity at the start plus the acceleration times the time. That's our interpretation. It's a relatively straightforward interpretation, even in English. The amount I have is whatever I started with plus how much it changed. But this is pretty powerful because it says that if I know the acceleration is constant and has some value, and I know how fast I was at the start, I can predict how fast I am at any other time. Alright, so as a reminder now, we have a is some constant, and v is v0 plus at. In the special case where the acceleration is constant, we'll also have that the average velocity is the so-called mean velocity, where the mean is what you're used to from what we usually call average in sort of other math classes, where it is basically the initial velocity plus the final velocity over 2. So for instance, if I had started off at 10 meters per second and I ended going at 50 meters per second, then my mean velocity is just 10 meters per second plus 50 meters per second all over 2, or 30 meters per second, i.e. it lies halfway between the 10 and the 50. In general, the average velocity, which is defined by how far something travels, is not equal to that mean of just the starting and ending values. But when the acceleration is constant, it is. And that allows us to go forward because the average velocity is defined as the change in position over the change in time. And so putting these two things together, I can say that x minus x0 over t minus 0 is the same as v0 plus v over 2. And that's sort of useful. Then we can solve this over and say, well, we bring a t over, and we get that x minus x0 is v0 plus v over 2 times t, which I want to remind you is just saying it's v average times t, which we sort of knew from this equation. But now we can solve it just a little bit more, and we can say that the final position is the initial position plus v average t, which is the initial position plus v0 plus v over 2 times t. So a whole bunch of algebraic rigmarole there. Doesn't seem to have helped us all that much. Most importantly, it's sort of a problem in that it doesn't depend just on my initial values and t. It also depends on this final value of v, so it's not particularly satisfying to us, and it's not where we're going to stop. So we have a equals a constant, and then we had v equals v0 plus a times t, and we just ended up with that x is x0 plus v0 plus v over 2 all times t. And the trick we're going to do now is we're going to take this value and plug it into that place and see what comes out. So we'll have x equals x0, that didn't change, plus v0 plus v0 plus at, all of that over 2 times t. And then we just start doing, again, some algebraic rigmarole. I have v0 plus v0, so that's 2v0, and then I have at all over 2 times t. And now I'm going to split up the inside. I'm going to have x0 plus 2v0 over 2 plus at over 2 all times t, which is going to become x0 plus v0t plus 1/2 at squared. And that is sort of the last major kinematic equation. It is the thing that gives us the parabola as our distance plot, x versus t, for constant acceleration. Earlier, I guess we theoretically had over here that we got a line on a vt plot, because I have a constant plus a slope times the variable. Okay, there's one last very useful but kind of grungy one to go. And it is not particularly pretty to get. We're going to return to our earlier equation, which was that x equals x0 plus 1/2 v0 plus v times t. And what we're going to do here now is, instead of eliminating the v, I'm going to eliminate the t, and that will connect my position and my velocities and eliminate the time, which can be very useful. But like I said, is not particularly pretty. So x equals x0 plus 1/2 v0 plus v, and now I'm going to go back up to this equation, and I'm going to solve it for t instead. And what I'm going to end up with is v minus v0 over a. That's if I resolve this and I say, oh, okay, I bring v minus v0 equals at, and then I divide by a, and I get that t equals v minus v0 over a. What does that get us? Well, I'm going to do another little trick just to save some time for us. I'm going to make this x minus x0. That's kind of traditional for reasons that might be useful to you, might not. And then I'll have, when I group this a little bit, I'll have 1 over 2a, and then I'll have a v0, or really, v0 plus v times v minus v0. I'm going to rearrange this in a completely silly way, but I'm just going to swap the order. And I'm going to call this v plus v0, and then this is v minus v0. And I'm going to do that because of a thing you might remember from algebra, hopefully, which is what's called the difference of perfect squares. So we might say that we have, in general, if I have x plus y times x minus y, and I just do out the thing by FOIL, I get the first one squared minus the second one squared. Putting that together, we'll have x minus x0 over here is 1 over 2a, and then we multiply out and we say v times v is simply v squared, and v times minus v0 is minus v0v, and v0 times v is plus v0v, and then finally v0 times minus v0 is minus v0 squared. So these are our equations so far, and we're about to be finished. But that last one in orange is x minus x0 is 1 over 2a times this mess, which is v squared plus v0v minus v0v minus v0 squared. And so we see that these two terms combine to go away, and I'm left with that x minus x0 is 1 over 2a v squared minus v0 squared. And then it's sort of traditional to solve this over and instead say we multiply through by 2a and we get that v minus v0 squared is 2a times x minus x0, which, is useful. It's especially useful when you don't have and don't care about the time. The classic example for these things is stuff like stopping distances, where you have something like a car is going 20 meters per second and brakes at 5 meters per second squared. How far does it travel? In fact, let's just do that as an example for this. So we have a car and it's going at 20 meters per second, and then eventually it stops because it was decelerating at 5 meters per second squared. And the question is, how far does it travel? Its so-called stopping distance. So we say here pretty easily we have that v squared minus v0 squared is 2a x minus x0, and we can write in some of these guys up. We end at rest, and we started at 20 meters per second, which we square, and then that's equal to, well, we know that our acceleration is minus 5 meters per second squared. Why the minus? Because, of course, we're going against the velocity. And then finally, we end up with x minus, and we'll just say we started at the origin because we have complete options there. And so we're left with, when we put everything together, that minus 400 meters squared per second squared is equal to minus 10 meters per second squared times x, or x is 40 meters. It would take about half a football field, a little bit less, for this car to stop, because 20 meters per second is relatively fast. The nice thing here is we could say, well, what if it had been, going twice as fast, in which case it would have had a 40 instead of a 20 meter per second speed, and that when we double that and then square it, we get 4 times as far, so it would end up being 160 meters. And we can see that right away without having to say, oh, it takes this long and then it travels this far and so on. So that's the use of that equation, but as noted, the derivation is not so great.